Today I'm going into the laboratory to test out Newton's second law. Most people know Newton's second law as F equals ma. Force equals mass times acceleration. Beautifully simple. I'm going to take several masses and I'm going to supply the same force to each one. When the mass starts to move, I'm going to measure its acceleration. This will give me enough data to put F equals ma under rigorous test. Does it stand up to examination in the real world? Let's go and find out.
Here's the setup. We have a low friction cart sat on a low friction track. The cart will be the mass in our experiment. The blue motion sensor sends a radar beam along the track and is able to determine the position of the cart at any instant. The computer can use this data and its internal clock to calculate the velocity at any given time, and hence produce a lovely velocity time graph in real time. Let's not forget the other end of the track. Here we have a low friction pulley from which I will hang a 50-gram mass. The weight of that mass will pull the cart along the track, causing it to accelerate. An accurate spring balance tells me that the force of gravity pulling down on this mass is 0.49 newtons. This accelerating force will remain constant throughout. The only thing I'm going to change is the mass of the cart, and we'll see what effect that has on the acceleration. Here I am checking the setup. If I give the cart a push, it should travel at constant velocity if the track has negligible friction. Let's see. Well, here's the graph. It's unbelievably good. The velocity is beautifully constant. Surely there must be some friction. What's the explanation? I admit it, I cheated. If you look here, you can see that I placed some boards under the track. I tilted the track until the cart definitely did travel with constant velocity. I was using gravity to compensate for friction. That's a neat solution. So now I get ready for the first run. Connect up the hanging mass. And away we go. Whoops. Now I'll show you the graph plotted in real time. Strange shape. Can you interpret it? This bit is just noise, where I'm holding the cart with my finger, about to start. This is the important bit. It shows velocity increasing steadily with time. This is the acceleration caused by the hanging mass. This bit is interesting too. You can see its constant velocity. This is when the weight hits the floor. The cart is no longer being pulled, it doesn't accelerate anymore, and travels with constant velocity. At the end, the cart comes to a complete stop. Okay, I better take a few more results. Here I go. I was so wrapped up in the experiment that I forgot that I'd left all that debris on the front bench. Sorry about that. And did you notice that I've got the problem of stopping and starting the computer on every run too? See the brass masses sat on the cart? That's how I increase the mass for each run. Here are the results from my 7 experiments. You can see that the overall shape of each graph is similar. If you look at the positive slope of each graph, you can see that there's a difference, indicating a different acceleration for each run. Let's have a look at this in a bit more detail. I've separated out the initial run. First, I select the part of the graph representing acceleration. Then I ask the computer to apply a linear fit to my pretty good straight line. And there you can see that not only does it provide a linear fit, but it also calculates the slope of the graph, which is the acceleration. In this case, 0.856 meters per second per second. Here's run number 3. I'll do the same thing. Select the acceleration part of the graph. Apply the linear fit, and there's the new acceleration. Very satisfying. Here's the 7th and final run. Doesn't look quite so good this time, does it? Anyway, let's jump ahead to the linear fit, and there it is. Let's have a look at all the results together. I've tabulated all the mass and acceleration data, but just have a look at this bit. You can see that the initial mass in the experiment consists of the cart plus the hanging mass. It's important to remember that the accelerating force accelerated the whole combination, the cart plus the hanging mass, as they were tied together. If you look at the graph, as expected, there's an inverse relationship between the acceleration and the mass. As the mass increases, the acceleration decreases. But we want something a bit more useful than this graph. Now I've plotted acceleration against the inverse of mass, 1 over m, and we have a beautiful straight line that goes through the origin. We can say that acceleration is inversely proportional to mass. Let's do the full analysis. The graph is of the form y is inversely proportional to x, or y is equal to a constant times 1 over x, where the constant is the gradient. If we apply this to our graph, we get acceleration is equal to a constant times 1 over mass. Let's rearrange that. The constant, which is the gradient, is equal to ma. But wait a minute. Newton's law says F equals ma. So if Newton's law is correct, F must be equal to the gradient. Now the exciting thing about this is that our experimental results allow us to check this out. Does F equal the gradient in our experiment? Does Newton's second law work? Let's see. We already know that the accelerating force F was 0.49 newtons. And Excel can work out the gradient for us. Here comes the equation for the graph, and the gradient is 0.48 newtons. Very close. That's very satisfying, especially for a one-man band performance. The slight discrepancy is probably mainly due to changes in the internal friction of the cart as the mass was increased. Well, that's the end of the video. I hope you got something out of it. If you did, please let me know in the comments below. And if you've got any suggestions about how I can improve the videos, I'd love to hear them. So, thanks for watching. Maybe I'll see you next time. Bye.